Silent drill. All right, thank you, ma'am. Thank you all for showing up. We've done some really cool work on swarming, both on flat surfaces and on curved ones, and I'm really excited to share it all with you. Before I get started, I just want to thank a couple of people. First off and foremost, my advisor, Professor Medynets, has put a ton of work into this project. I'd also like to thank Professor Popovici, because she showed us some things about the system that we're studying that we didn't think were even possible. I'd like to thank Professors Alevros and Price for reading my paper. And I'd also like to thank Dr. Ira Schwartz at NRL, because he's the person who really introduced this system to us and showed us how it works. So the way that we try to understand the systems that we're going to study is called dynamical systems. So a dynamical system for us is just we use continuous systems. And basically, we just have a number of points in space somewhere, and they move according to some equation of motion. So for example, you might control the velocity or the acceleration of the points. And so the questions that we're trying to answer are what happens in the long term to the system that we're studying. So systems like this have been studied pretty much since calculus was invented. So Isaac Newton studied the motion of the planets with his law of universal gravitation. And what he noticed was that if you have two planets moving according to gravity, you can figure out exactly where they're going to be at any point in time. So all you have to do is sort of integrate this differential equation and find a solution, and then you'll have the answer. And so sometimes it might look something like this. So after two planets, his next question was, well, what about three planets? So he tried it, but he never really got it to work. And a lot of people since him also tried to figure out this problem. It was called the three-body problem. How can you predict the behavior of three planets moving according to just gravity? And so as you can see with the figure on the right, it's not always very easy to see what's going on. And in fact, it's been proven that not only can you not come up with a function that tells you where the planets are going to be, but this is actually a chaotic system. So in the long term, it's pretty much impossible to predict almost anything about where the agents are going to be, where the planets are going to be. But all's not lost. So although we may not be able to completely characterize what's going to happen, we can use other parts of math to figure out what's going to happen to the planets in the long term. So for example, we know that in physical systems, momentum is conserved. So even though these planets have all these weird trajectories, if we look at the center of mass of the system, it moves in this straight line. So it moves at a constant speed in a straight line like that, and it will keep doing that forever. So although you might look at that system and say, well, there's nothing that we can say about it, actually, we can learn a great deal. So systems like this have been studied by a lot of people, but here's three that I want to talk about in particular. Henri Poincaré, who's on the left, he sort of was one of the pioneers of this dynamical, continuous dynamics theory. And in fact, he was the first person to realize that this three-body problem ended up with a chaotic solution. In the middle is Alexander Lyapunov, and Lyapunov invented a number of different methods for dealing with systems like this. So if you can't solve exactly what's going to happen in the system, what can you find out? So one example is called his direct method. And essentially what you have to do is come up with an energy function. So here we've called it L. And if the energy function is decreasing over time, then you know that in the end the system will evolve to a state where it has the minimum energy. So the problem with Lyapunov theory is that you can't always find the energy function. It's not obvious what it is. So in physical systems, sometimes it's obvious. But if you make up your own dynamical system, it's not necessarily clear what the energy function is going to be. So he also came up with an indirect or linearization method. And that's the second method here. And what all that stuff on the right means is that if you linearize around a point, you can construct a system that you understand. And so if you're close enough to a certain point, you can understand the behavior of that point sort of by automatically generating an energy function. The problem with this is that it only works locally. So this will only tell you what happens really close to the point that you're studying, but it doesn't tell you anything about the entire system necessarily. And so Lassalle, who's pictured on the right, he generalized the direct method into the form that we're actually going to use it in. So the swarm that we're studying is called the parabolic potential model. And so the equation of motion is pictured on the top. So every agent, so all of these points represent individual agents, so they might be birds or they might be robots. And every agent's acceleration is given by this function. So what the part on the left means is that if the speed is below 1, then it's going to accelerate. The speed's going to increase. And if the speed is above 1, then it's going to decrease. So all of the agents will try to keep their speed around 1. And what the term on the right means is that every agent is attracted to the center of mass. So there's a vector that points from each agent to the center of mass of the whole system, and they're pulled in that direction. And so I might be able to convince you that in this system what happens is you'll eventually get a sort of orbital motion, where the agents are all trying to go in a straight line at a constant speed, but they're constantly being pulled in towards the middle. And indeed, most of the time when you simulate the system, that's what you see. So this is a simulation of the system with random initial conditions with 10 agents. And you can see that this center of mass is going to stabilize. It's going to stop. And then all these agents are going to end up moving on this circle, either in one direction or in the other. Now, this system's been studied before. It's been studied at NRL, and it's also been studied, it's been studied by a bunch of people. And so they have noticed another thing that the system can do, which is straight line translating motion. So if you start off the agents with a very particular velocity vector, they actually don't do this. And instead, they just go in a straight line with this weird sort of wavy figure 8 behavior. But people originally thought that this was sort of something that we could neglect. It was something that wouldn't happen very often. And so really, in general, this is what's going to happen most of the time. And so that's what we thought as well. But about halfway through the project, we saw some very strange behavior. So this is 3 agents that we set up with certain initial conditions. And they're not doing anything that we recognize. Right? They're doing a completely different behavior. And so what this means is essentially, maybe it's not as simple as the system always evolves to do this. So in order to understand the system, we wanted to sort of break it down and understand what's going on a lower level. So we figured, OK, more or less always, we expect the center of mass to stop. And if the center of mass stops, let's just fix it. OK, so let's take the origin, let's take the point 0, 0 in the plane, and pretend that that's the center of mass, and just have one agent orbiting that. And let's see if we can understand the dynamics of that system. So that's this differential equation, but we just drop the big R. So this is a 4-dimensional system because we have the agent's x and y position, and we have their x and y velocity. So we wanted to reduce the dimension of the system into something that we could understand more intuitively, because 4 dimensions is hard to really think about. And so we use this substitution to turn it into a 3-dimensional system. So this number u is going to be the square of the distance from 0, the square of the distance from the origin. This vector v, or this scalar v, is going to be the square of the speed. And w is going to be the dot product of the vector from the origin and the speed. And so what we expect is that the agent's going to end up rotating around the center of mass. So the speed is going to be 1, the distance from the origin is going to be 1, and the dot product is going to be 0 because the 2 vectors are orthogonal. And I'll show you a picture of that behavior. So here's what we expect the agent to do. So you start it off in some random initial configuration, and eventually it's going to end up on this circle. So in order to prove it, we had to come up with this Lyapunov function. And like I said earlier, we didn't just find it in a day. It took about a month to figure out really what this function had to be. And it's not a completely random guess. So the u plus v comes from physics. Physical systems tend to have energy that's given by that. And then the logarithmic function was based on some intuition about the Cauchy-Schwarz inequality. But what you can see over here, so this is the system in our normal coordinates. And then if we take it into uv and w space, right? So this is the u-axis, this is the v-axis, and this is the w-axis. You're going to start somewhere, and then in the end, you'll spiral towards this point. And so sure enough, the Lyapunov function is less than or equal to 0 everywhere. So we can apply Lassalle's theorem and prove that this point is actually is globally stable in these new coordinates, which means that the ring configuration is globally stable in the old coordinates. So this is a graph of the Lyapunov function over time, and you can see that it'll stop, it'll sort of be stationary, but then it will keep going down and keep going down and keep going down until it approaches this final value, and the value is 2. And what that value, the only way you can get to that value is by being on the ring. There's a different coordinate system that's a little bit more complicated that you can use to show that if you start off turning left, then you'll keep turning left, and if you start off going right, then you'll keep going right. So now we're going to transition back to talking about multiple agents. So we have our old equation of motion where all of the agents are being pulled towards the center of mass. Now, we wanted to apply Lyapunov's indirect method because we know that globally the behavior is not stable, right? You can get other behavior besides the ring state. So we want to turn the ring state into a point and prove local stability by using this linearization method. So the way that we do that is by applying these new coordinates. So this is the center of mass, and this is our agent. And so u is going to be the distance from the agent to the center of mass. Theta is going to be this angle from the x-axis. Phi is going to be the angle between the position and the speed, and then v is going to be the speed. So we know that the ring state will correspond to this point, where the distance is 1, the speed is 1, and this angle here is pi over 2, or that's 90 degrees. We also know that the sum of all the cosines is going to be equal to 0, and the sum of all the sines is going to be equal to 0, because that guarantees that the center of mass of the system actually is the center of mass of the system. So we believe that no matter how many agents you have in the system, that the ring state is locally stable. And so we use that coordinate substitution with a little bit of dimension reduction to prove that this is true for 2 or 3 agents. But once you move up to 4 agents, there begins to be a problem, right? So the Lyapunov's indirect method only works if any change to the system means that you'll go back to the original position. The problem is there are changes to this system that won't go back. So for example, if your agents are in a ring state like this, you can cleverly shift all of the points to keep the center of mass the same, and then so you'll go from the black positions to the white positions, and there will be no reason why the system will want to go back. It's still on this ring behavior. So right now we're trying to reduce the dimension of the system further using a mathematical theory called center manifold analysis. So now I'm going to switch gears a little bit, and I want to talk about manifolds. So we understand a little bit about this swarm on flat space. And in fact, lots of different swarm models have been studied on flat space, so in the plane or in ordinary 3D space. But nobody really understands what goes on in other spaces. So if, for example, you had a swarm and you wanted them to move on the surface of a sphere, right? Nobody would really understand how to do that. And the thing that originally motivated us to do this was we wanted to change the limit cycles of this swarm. So rather than getting a circle at the end of the behavior, we wanted to get maybe an oval or a figure 8 or a heart shape or something like that. So this is an example of what we want to do. So in order to do that, we have to use this theory of Riemannian manifolds. And you can think about a Riemannian manifold as basically just a surface. So the Earth is a Riemannian manifold. And the real thing that's different between flat space and Riemannian manifolds is that we change the way that you calculate distance. So we've been taught that you calculate the distance between 2 points using Pythagoras' theorem, right? And you calculate the size of vectors, for example, using Pythagoras' theorem. But here, we decide that we're going to change that, and we're going to calculate them using some other method, right? So for example, here, so this is ordinary Pythagoras' theorem in flat space. But over here, we have some different way to tell the distance between points, or to tell the length of a vector. And so the really big takeaway from this is that it changes what a straight line means. So in regular space, a straight line is the way to minimize the distance between 2 points. So if you have 2 points and you draw a straight line between them, that's the shortest path that connects those 2 points. But if you've ever taken an airplane flight, you know that that's not the case in general. So if you're on the surface of a sphere, you might want to hug the land like this. And Stephen Strogatz talks about how when he was a kid, he used to think that the land was safer, and that's why they were doing that. But it's not, actually. So the reason why they do that is because there's less space up here than there is down here. Right? This length is longer than this length. And so that means that you have to draw your paths differently when you're trying to draw the shortest path between 2 points. So on a sphere, this is the new Pythagoras' theorem for a sphere. On a sphere, the shortest distances are called great circles. I think I learned that in nav class. But there are a lot of other geometries where the shortest distance is something else. So this one is another one called hyperbolic space. And in hyperbolic space, there's a lot of space sort of jammed down here. So the lengths down here are very large, but the lengths up here are very short. So a straight line in the hyperbolic space would be a semicircle, right? So they look like this. And in math, this concept of a straight line is known as a geodesic. So we have our original system. This is our original system. And we want to change it a little bit because we want it to really work on the surface of a sphere. And there's 2 things that we really have to change. First off, when you're moving from one point to another, so when agents are attracted to each other, they should be attracted along geodesics rather than along straight lines. Because if they're attracted along straight lines, you could just draw a different map and they would be attracted in a different direction. So we need to change this vector on the right into a geodesic. And we also need to ensure that if the swarm is not under any external force, that it moves along a geodesic. So if the swarm just keeps going in a straight line, this has to be a straight line in our new geometry, not a straight line in our old geometry. And so we did this and formulated this new system. So this is still the acceleration of each point. And this now is the norm of the speed, right, or the square of the speed in the new coordinates. So if you're high up on this old hyperbolic geometry and your speed is this much, then that would be smaller than here. So we have to account for that. This over here is called a Christoffel symbol. So this ensures that if there's no other acceleration, the agents will indeed move on a straight line, or on a geodesic. And then on the right, this entire term is a way of saying that we're taking the gradients, the gradient of a distance function, right? So this u tells you the square of the distance between 2 points, and then we take the gradient of that to ensure that we're actually attracted along the direction that minimizes the distance. So I bet you're thinking, Carl, when are you going to show me a video? So I'm going to show you a video. This is an example of our gradient swarm. Now it's on a new manifold. So these are, you can think about this like a latitude and longitude map. And over here, this is us projecting the swarm onto the new surface. Now, we did all of the actual math over here. So these agents don't necessarily know that they're on a sphere. But when you apply the right sort of metric tensor and the right functions, you can make them move so that when you project it back onto a sphere, it finally makes sense what they're doing. So they start at sort of random positions. And you can see over here that they're going to stabilize into this strange shape. So you might wonder, what is that? But then when you project that over onto the sphere, you can see that actually they're turning into a circle in the new geometry. So we've done this on the hyperbolic plane as well. That's the plane that has the semicircular geodesics. And here's an example. So over here, we started with initial conditions that were far down. And over here, we started with the same initial conditions, but just shifted the entire system up a little bit. And so ideally, what we would want to see is for our circles, they'll still look like circles, but we want them to be bigger the higher shifted up they are. Right? And that will imply that really this swarm is moving according to the rules of our new geometry, not our old geometry. So let's see it. So again, you can see that the initial conditions are the same, but they're starting to do something a little bit different. And so now the rotation is really beginning. And you can see, sure enough, that the limit cycles do what we expect them to do. Right? We get a small circle down here and a big circle over there. And in our new geometry, those two circles are actually the same size. So I promised you this, right? We were going to use this to try to figure out how we're going to get a differently shaped limit cycle. And it turns out that actually there are a lot of limitations with what changing your geometry can do. So you can change your geometry to make your circles look a little bit different. But essentially, you can't make them that different. You can't turn them into figure eights. You can't make them concave. So there's something called a flat metric tensor, which essentially is a new manifold where we just take the old space and stretch it. So that's what we've done. We've taken the plane and we've stretched it according to this matrix. And now we'll see the agents start to move. So again, they started at random initial conditions, but now they're moving on to our new limit behavior that is what we wanted. And we can turn this into any orientation of oval. We can make it as long as and skinny as we like. Okay, so the last thing that I did in this project is I saw Jack Gaynor's presentation and I thought that we wanted to do something kind of cool too. So we put together some simulated drones. So this is a system where we want these robots to move according to these differential equations. So we solve the differential equations in Mathematica, which is sort of like a pure math programming language. And then we use Python to have Mathematica talk to ROS. And ROS is the robot operating system, which you can use to operate robots in the real world. Now, we didn't have any robots in the real world. So instead, we simulated some in Gazebo. And ROS and Gazebo talk to each other sort of formally as though Gazebo is actual robots. And so you can see what happened. So this is our code. We're about to run it. Okay, and so you can see our agents are taking off. So we want them to move onto a plane that's 5 meters off the ground, and then we want them to start doing the thing that they were doing originally. And so I'm going to speed it up for you in a second so that you don't have to wait through the entire thing. But you can see them sort of start to figure out what they're doing. They're trying to get onto this plane, and they're trying to obey this equation of motion. And eventually they end up stabilizing into this nice limit cycle, like that. There it is. And so sure enough, the things that we studied, you can implement them in the real world. And in fact, having some idea and some proof of what they actually do really helps you make those decisions. That's all I've got. Thank you. Yeah, Mike.
So can these agents ever run into each other or hit each other?
Sure. Yeah. So that's a good question. So in the original simulation, so when we do the mathematical simulations, you'll notice that there's hang on, let me find it. Yeah. So this one, they just go straight through each other, right? So that's the way that we model them in our ideal space. But of course, you can't have robots just go through each other, at least not yet. So these ones have obstacle avoidance built in. And that's why, in the end, you see that they only end up rotating in one direction. Yeah, so that's why you observe that. Yeah?
It's like in your video app, maybe it's just the way it was. The oval, got into the oval shape much quicker than hyperbolic space or any other system than just pure circle.
Sure. So there's actually a lot that we don't understand about the swarms on manifolds. They behave in a sort of weird way. And so you'll notice, one, they stabilize like that. And two, they're all moving in the same direction. And we don't know why that is. But we have some suspicions that it's due to the way that the initial conditions are translated into the new coordinates. So it might sort of just be a coincidence with the way that we set up the program. But it could be something else. We don't know. Yes, sir.
Can you go to your slide 4?
Sure.
Sorry, this is going to be a physicist question, but so your equation of motion here, I mean, it's a non-physical equation of motion, right?
Yes, sir.
It's weird that your center of mass just sort of stops.
Yes, sir.
Right? So is there a reason that you chose a non-physical equation of motion?
In a way, so if we chose some sort of gravitational interactions, for example, that problem has already been studied, one, and two, it's also...
But in a physical, you can come up with potentials that are just not simple central potentials. An elliptical potential.
Sure, so maybe a system where energy is conserved, for example, or momentum?
Energy is conserved, or for example, orbits in a sophisticated gravitational potential, not a simple spherical central potential.
Sure, yes, sir. So the thing that really causes the center of mass to stop, the reason why we don't have conservation of energy or conservation of momentum, is actually the nonlinear velocity term.
Right.
And so the reason why we have that is just because this term is included in pretty much every swarm model there is. So there are lots of swarm models that use other potentials. An example is the Morse swarm model, which more closely mimics what birds or bees or something do. But the nonlinear velocity potential is meant to really, you can think about it like the agent's comfort. So the agents want to move at a certain speed. They don't want to just stand still. But at the same time, they can't go that fast. Maybe they're birds or something. It's just sort of again, I mean, you could come up with any sort of velocity term that you wanted, but this is one that hasn't been studied. In a way, that makes it harder. That's why we have to come up with these new energy functions, and we can't use old ones. Awesome. Thanks, everyone.